Okay, welcome to the Galileo Masterclass Brazil 2022. We'll start today with the first lecture of the first part. The first part will deal with GNSS signals and signal processing, so the first six lectures. And afterwards, you will get to know data processing methods and positioning, and also there are a lot of expert talks in between during these couple of days that will highlight special features of Galileo, will introduce the European Space Program, and so on. So let's start with this first lecture today, this morning, on multiple access for GNSS. So this is the first lecture on signals. Yeah, so this is the outline of the first lecture. So first we'll talk about multiple access schemes. What is multiple access and what kind of schemes are available? Then we talk about spread spectrum signals, and then in the end about the processing gain and interference. Yeah, several satellites of GNS of satellite navigation systems. They need to share the same transmission medium, and they broadcast to the GNSS users to enable positioning. The satellites need to share the transmission medium such that the GNSS users can separate the different satellites, perform ranging, and receive the navigation data. The satellites need to share the available bandwidth by using channel access or multiple access MA techniques. MA techniques have the aim to ensure that the signals of the different satellites will be separated or even orthogonal. In our case, the schemes will not be orthogonal for GNSS because the system is asynchronous. In general, there are three basic MA techniques. Time division multiple access, so TDMA, frequency division multiple access, FDMA, and code division multiple access, CDMA. Here's a schematic of these three basic techniques. There's also a fourth technique, space division multiple access. If you have multiple antennas and on the transmitter and receiver side, then you can also try to separate users by spatial filtering, so in space. But the basic techniques are TDMA, FDMA, and CDMA. So in the upper left corner, we can see the TDMA schematic. So the different users here marked in different gray shades, they transmit in time slots and they use the complete frequency band available to transmit, but in turns in these slots, in these time slots. On the upper right, corner, we see the frequency division multiple access scheme. Here, the users transmit in using subbands. So each user uses a chunk of frequency band available and transmits all the time. So this is a broadcast scenario. And then we have also in the bottom code division multiple access. Here, all the users transmit all the time and they use um, the complete frequency band available, but they are separated by codes. Yeah, in principle, each of these techniques can achieve the same aggregate spectral efficiency. So what do we mean with this? A symbol rate per user of the channel, number of users per channel, and the sum symbol rate is the same for all these techniques. So none of these techniques in this sense are better. Uh, they just have different properties, and you can select these techniques according to the system that you are trying to operate. These basic MA techniques can also be combined. Yeah, so we can also create frequency, time division, multiple access, frequency division, code division, multiple access, and so on. So for GNSS in general, we can consider the following, or we have the following side constraints on the system. So the number of in-view satellites So the broadcast users is quite low, around maximum 12 per system. We can see at the same time or receive at the same time, dependent on time and the position on Earth, and the masking angle that we consider. So it's a rather small number of users that have to share the bandwidth. Data transmission demands in general do not play a prominent role. So we don't need to stream videos from our GNSS signal. So the data that we have to receive from the satellite to perform positioning is not a lot of data, and the data rate in general can be slow because we are receiving the data with corrections and propagation information. Mainly other performance measures have to be considered when choosing the appropriate MA technique. So for GNSS, different properties are important than for communication systems. And these things or these characteristics are so signal properties for GNSS. It's very important. We're performing synchronization in a GNSS receiver. So we are estimating time delay Doppler phase of a received signal, and we will try to synchronize our receiver to the system time of the GNSS. So synchronization accuracy is very important. Synchronization robustness, so we want to do this synchronization in a robust form without large errors. We want to have over a long time a stable synchronization, estimation process, and so on. Inter-system multiple access interference, so MIR or spectral separation are important. So inter-system interference means interference between different global navigation satellite systems. So the interference between GPS and Galileo, the interference between GPS and Beidou, and so on. Then also the intra-system multiple access interference, MIA, has to be considered. Um, in the beginning, GPS was alone in the current L-band frequency bands that are available for global navigation satellite systems. GLONASS, the Russian system, was well separated spectrally from GPS. So in the beginning, GNSS, we could say, was a noise-limited system only. And the intra-system multiple access interference was quite low because we had only a few satellites interfering with each other. Now we have all the systems, they are introducing more signals on the same carrier. So GPS, for example, introduced more signals. This is also true for Galileo and for other systems. So they increase also the intra-system multiple access interference with these new signals, having more signals, increasing the power of these signals. So MIA will become in the future a more prominent issue. And then in general, interference is always an issue in GNSS because the received power of the signal, the received power is very low. So any kind of in-band interference is very harmful, also at very low levels already very harmful to GNSS. Multipath performance, also very important. This is a little bit related to synchronization robustness. Um, any kind of, because a multipath signal is like a delayed copy of the signal coming from the satellite, but here then maybe reflected by a nearby house. Then it will be more difficult to synchronize to estimate the time delay, Doppler carrier phase of the line of sight signal of the satellite, and thus we will have positioning errors. And many some other issues are very important for signal design and also for then the choice of multiple access techniques. So most GNSS, GPS, Galileo, Beidou use direct sequence, so CDMA. code division multiple access, DS-CDMA. Each satellite uses a different code for transmitting its signal. Spectral separation between different GNSS in the same frequency band can be achieved by usage of different modulation schemes, and we will see this in the following lectures. So in principle, these systems, they have implemented an FD-CDMA approach. GLONASS, the Russian system, is the only system that has implemented a CD-FDMA approach. So they have FDMA. Each satellite uses a different subband of the available bandwidth, and transmits the same spreading sequence within this available bandwidth. So here we can see in this slide what I mean with the FD-CDMA approach. So we can see here the GPS-CA code signal in black, the GPS Galileo Open Service, so the GPS modernized Open Service, and the Galileo Open Service in blue. The future or modernized GPS military service in M code, the M code signal in green, and we have the Galileo public regulated service in red. And you can already see here the spectrally separated signals. So the military signals are all, and the public regulated service, they are spectrally separated. Even the GPS-CA code is spectrally separated from the modernized GPS and Galileo Open Service. So the providers of different, this is just an example of L-band. There's much more signals present in this band, but we can see here as an example how the GNSS try to separate their signals spectrally. The spectral separation between authorized and open service, so military service and open service, has also another important meaning, because in case of a crisis, you want to jam the other military or authorized services and open services without jamming your own military service. So all the military services seek to being spectrally separated from open services and other military services.
Yeah, spread spectrum signals. So we have here a small or a model of the signal in time domain. So X is the received signal of either a direct sequence CDMA or CD-FDMA baseband signal. Then we have here the power, the square root of P is the square root of the power. We have a binary navigation message data, G of T, delayed by tau, which is the time delay of the signal that it's experiencing during propagation. And we also have the pseudo-random spreading sequence. This is the sequence that helps us to separate the signals at the receiver. And we also have some noise here. White Gaussian noise with power spectral density of N0 half. The PR sequence we can further describe by this model. So we have a sum of data bits of the sequence. They are called chips, and they are binary. These data bits or code bits D of M. Then we have here the chip duration, the square root of TC. We have here a Dirac delta function delayed by MTC. And this is convolution with a chip pulse shape. So we have a pulse shape which is not necessarily restricted to be time limited to only one chip. So we have maybe inter-chip interference also of these pulse shapes. Then we also have here ND, which is the number of chips per PR sequence, because the PR sequence has a certain period and is repeating over time. Yeah, the PR sequence can be assumed simplified to be a zero mean, so the expectation of DM is zero, and so-called wide sense cyclostationary, so WSCS sequence with the expectation of DM-DL conjugate is the autocorrelation function of the sigma sequence M L minus M, and the autocorrelation function of the sequence M L minus M is periodical with ND here. So we have integer numbers of P. We have the same autocorrelation function here. We also assume in the following that the integral of CC conjugate over one period of the sequence, and thus the integral over the power spectral density of the sequence is 1. So we perform some kind of a power normalization of the sequence. Yeah, the autocorrelation function of C of t can be given like this. So the autocorrelation function of the sequence is called RC of epsilon, and this is the integral of 1 over TD minus TD half to TD half, C conjugate T minus epsilon. We can use Parseval's theorem to translate this into the frequency domain. Then we have the power spectral density of the chip pulse shape times the power spectral density of the sequence. That's phi of d. And then we have an exponential function of j2 pi f epsilon. And the integral is with respect to the frequency. And if we assume that the power spectral density of the sequence is 1, which means that the sequence is random, which is a reasonable assumption for GNSS. In our case, I mean the sequence is pseudo-random, but we can model it as random. Then we can see that the autocorrelation function is only dependent on the chip shape again. So which is interesting for our discussion in the following. Again, we assume that the chip shape, the power of the chip pulse shape is equal to 1. Yeah, based on this model of the autocorrelation function, we can conclude that the problem of optimizing cross-correlation and autocorrelation properties of the pseudo-random sequence, the M, can be treated separately as 2 different problems. So we can optimize the WSCS sequences and their properties in one problem, and we can also optimize the chip pulse shapes, and we can only optimize the chip pulse shapes with respect to the autocorrelation function in our case. And with this, we will see later also the synchronization performance of the signal. We can also use the chip pulse shape to implement the FD in the FD-CDMA. So the different chip pulse shapes, they will have a different frequency support, and we can use the different chip pulse shapes to implement the spectral separation of signals. This result also, we can conclude that this gives us the possibility for easy analysis and understanding of the properties of chip pulse shapes and PR sequences. In the following, I will concentrate more on the chip pulse shapes. There's a whole field of designing sequences. I will only discuss with you about this in one of the labs a little bit more in detail, but here in this lecture, I will now focus more on the properties of chip pulse shapes. Yeah, correlation. So in order to separate the different satellites in the receiver, we will apply correlation. So the receiver performs correlation with a period TD using a replica signal based on a model. In the following, we will assume that this model is equivalent. So the model of C is exactly equivalent to C. In reality, this is maybe not exactly to the model. So you have a standard where you can derive the signal, but the actually received signal coming from the satellite has a slightly different characteristic, and the characteristic of the signal arriving from each satellite is different. So each satellite has a different characteristic. If you look into the literature, there's a lot of discussion about signal biases or satellite and receiver biases. These biases are resulting from this mismatch of the model in the receiver. So if the receiver is using a model for the correlation that is not exactly matched to the received signal, you end up with a bias in your time delay estimate. And this is what is happening in reality, and you have to take care of this. But we, in this lecture today, we will assume that the model is exactly known, and that the receiver produces this exact model as you receive the signal, and then we can implement a model. Y of k is the signal after correlation. We implement here correlation periodic in one period, or for each period k. Of the received signal correlated here with this model, and we perform integration, which is then correlation, and we also have to perform correlation with the noise. And at the output of this correlation, we have the square root of p, the power of the signal, the navigation data at time instant k, and we have a noise term here. We assume here, or in the signal in general, this data bit or this navigation data signal does not change within one period of the PR sequence. So it's constant over TD. That's why we have here at the output of k at each time instant k, we have values of between of only -1 and 1. And the power of the signal and the noise after the spreading can be given as the expectation of G of k, which is P, and the expectation of the noise can be given as N0 over 2D, TD. Yeah, now we can introduce also the other satellites. This was correlation with only one satellite signal and noise. We can now introduce the other satellites. So here we have again the satellite that we're interested in with the signal, the spreading sequence C. We are using the model of C to correlate, and then we have also NSAT -1 other satellites with different pseudo-random sequences, CI. We correlate also with C, and the PR sequences are designed such that this cross correlation is very, very small. And this is the multiple axis, the intra-system multiple axis interference. However, you can assume, or we will assume for the time being, that this is close to 0. In reality, it's not, but it's very, very small due to the design of the PR sequence. And then we also have to correlate with the noise, and at the output we approximately now get the signal from this satellite of interest, the data signal from this satellite of interest G, plus the noise as we had before, as we would have received only one satellite. I mean, in our case, this is now approximately here because the correlation with the other satellites is only approximately 0. By using different models, so of CI, now we can do this for all the satellites, and with this we can separate the signals for each satellite. In case of the direct sequence CDMA, the satellites are separated now using different PR sequences, while in case of CDFDMA, the signals are separated spectrally in these subbands of the FDMA axis or FDMA scheme. All satellites, in case of the CDFDMA, they use the same PR sequence. Yeah, we can now work towards a discrete signal model also. So we use a simplified receiver model here also. So we have here the antenna. We have some additional noise, so additive noise. We have a low pass filter, and afterwards some sampling, and we end up with a signal X of Kn plus N. I'm using here this index to also specify the periodicity of the signal in periods of K. We will have N samples. We can see this here. We have capital N samples per time instances per K, capital K periods. And we have a sampling duration TS, which in our case is then equivalent to 1 over twice the one-sided bandwidth of the signal. And this bandwidth is given by this low pass filter here, which is an ideal low pass filter. Here you can see the frequency representation and the time representation of this low pass filter. So the low pass filter is constant from minus B to B and is 0 else. Yeah, and with this model, defining that TD is equivalent NTS, so we have in each period of the sequence, we have N samples, each with a duration, and the sampling duration is TS, so TD is equal to NTS. And as the sampling duration is equal to 1 over 2B, we have here the relation of N over 2B for TD. We can now write our signal as a vector for each for each period. So we have in the vector X, we receive the samples over time for one period. We have then again the power of the signal, the square root of P. We have the navigation data changing for each period. We have the power, the pseudo-random sequence delayed by tau. This is now here also given as a vector that is delayed by tau each sample. And these are column vectors. Yeah, and we will assume for the PR sequence that the L2, the square of the L2 norm is n. While in general, depending on the delay, this is not exactly true. This can change. This depends on the waveform used or on the chip pulse shape used to modulate the sequence. However, in general, for example, GPSCA PR sequences with a bandwidth larger than 1 megahertz, this is a very good assumption. So we can stick to that here, that the square L2 norm of C is approximately n. And additionally, we assume that we have more samples than bit symbols, and these bit symbols are called chips. Maybe I didn't mention this so far. So we have more samples than chips usually, and we can, if we have also an integer number of samples per sequence, then the sequence is not changing anymore over time, right? We can see this as repeating blocks, these kind of sequences, and this makes our model more, let's say, tractable. This, you don't need to select this the sampling frequency like this, but for example, if we have 1023 chips and we choose a sampling frequency of 4 megahertz or 4,000 samples per period, so this will be always the same. We have always 4,000 samples per period, and we can then build in our signal model, we can consider this PR sequence as a block repeating vector. Yeah, we can also define autocorrelation function now in discrete time. So RC of epsilon, and now we have here these brackets. Now we correlate C tau with 0 to C of epsilon, and this is how we get the autocorrelation function. We also assume normalization of the sequence. So C transpose times C divided by N is 1. And the receiver performs correlation with a period of NTS, so TD, using a replica signal based again on a model. And we will assume again that the model is exactly replicating the signal received. So in case time delay is known and the correlation with other satellites can be neglected, as we have seen, this is implementing the multiple axis, so the CDMA the CDMA scheme. We can now define y of k equals 1 over n c transpose of tau, and we correlate with the signal. And then we have here the correlated part with the signal, and the correlated part, or the correlation with the noise. And then the result is then again the square root of p of the navigation data signal plus 1 over n c transpose times the noise. So we have again at the output the data of the satellite plus the noise, and it's separated from all the other satellites. Yeah, let's quickly talk also about processing gain and the interference. Multiplication of the navigation data sequence g of t in our continuous model with the much faster oscillating PR sequence c of t introduces a spreading of the spectrum of the navigation data sequence g of t of the factor s, which is often called spreading factor. And this spreading factor is the period of the spreading sequence divided by the duration of the chip shape. And in general, TC is much, much smaller than TD. So we have TC in nanoseconds, for example, and we have TD in milliseconds, for example, in GNSS a lot. And the spread sequence thus can be hidden below the noise in case the maximum value of the PSD of the noise n0/2 is larger than the maximum value of the PSD of the spreading signal. And this is also the case, and this is one of the origins of the CDMA technique also, or the spread spectrum systems in many years ago. Initially, people also used this kind of a technique to hide signals below the noise, because when you don't know the spreading sequence, you cannot receive, or you can even not detect the signal because it's below the noise. Only when you perform the correlation, the signal is then above, visible with an oscilloscope or a spectrum analyzer above the noise. Yeah, and this here we can see this spreading in a schematic. So we have the power spectral density of the navigation signal here, phi of g as the dashed curve. We can see that it's much higher in its peak than the spread signal phi of c, which is the power spectral density of the spread signal. And you can now assume, for example, that the level of n0 would be around here, where my cursor is. So the spread, when the waveform is spread, it's below the noise, and when it's despread, it's above the noise, because we have seen the result, the signal after correlation is just g of t times the power. So we have exactly realized this, that the spreaded waveform is below the noise floor and the despreaded waveform is above the noise floor. Yeah, we can also calculate this. This is what's called then the processing gain. So we have the two parameters, the processing gain and also the spreading factor. The processing gain is the relation between the SNR before correlation, SNRS, and we will also calculate the SNR after the spreading, after correlation, SNRD. So SNRS, we can calculate the power of the signal, which is the expectation of the L2 norm of the signal in vector form, which is equivalent to n times p. And we have also the expectation of the L2 norm of the vector of the noise, and this is n times sigma n square, and sigma n square is the variance of the noise process. And then we have p over sigma n square, and we can rewrite this, the noise power is n0 times b in our case, so p over n0 times b. In case the time delay now is known and we can perfectly despread the signal without any time delay error or bias, the signal after despreading is the expectation. Now we perform correlation of the signal and we take the absolute valued square. And we also look at the expectation of the noise correlated with the model. And again, here is as we had defined, 1 over n times c transpose times c is 1. Then the absolute valued square of the remaining square root over p times g of k is just p, because g of k is just 1 and minus 1. And in the denominator, we have 1 over n square, because we have here the absolute valued square. And we have here in the middle, then the only random part is the noise, because the C of tau is deterministic in this case. And this can be rewritten here, this expectation of n times n Hermitian. Hermitian is transpose conjugate here. So this H is the identity matrix of dimensions n times sigma n square. And in the end, as 1 over n times C transpose times C transpose conjugate, in our case, C is real, so the conjugate doesn't influence a lot, nothing. It has no influence. This is 1 again, so we remain with sigma n squared divided by n. And that's why we have then Pn times sigma n squared. Here we already see that the SNR is increased by a factor of n after the despreading. And we can reformulate this now here in the last line. We can introduce for n now Td times 2b, and we can introduce the noise power also n0 over b. We can redefine now 1 over Td times 2 is equivalent to Bd, and then we get here a new signal to noise ratio at the output of the correlator, and we see that the signal has the same power, but the noise power is reduced because BD is usually much smaller than B. So what the correlation is doing is in the SNR is reducing the noise power. And the processing gain in our case is equivalent to the number of samples that we use in one period, and then also related to the bandwidth of the signal of the spreading waveform. Yeah, and this is then the relation we can build. So we can say that the SNR after correlation is P over N0 BD. We can now introduce again B, so P times B times N0 times BD times B. And we can reformulate this now, and we see that this part here, P over N0 times B, is the SNR before correlation times a factor, and this factor is the processing gain. The processing gain now is the relation between B and BD, and we can build also a relation to the spreading factor, which is then 2 times R times TD divided by TC. And this number R is dependent on the time bandwidth product of the spreading waveform that we use. If we assume a rectangular pulse shape for the navigation data message, and the data message is binary changing with the code periods. Yeah, and to put it all in a nutshell here, the processing gain G is a result of the change of the noise bandwidth and the resulting noise power, as we have seen. And the spreading factor describes the spreading of G of T by multiplication with C of T, and the processing gain describes the gain in SNR after the spreading. This is how you can separate the two. A special case is, for example, if R is 1/2, then the spreading gain is equivalent, the spreading factor is equivalent to the processing gain. This is when you open some classical books on spread spectrum systems, they assume always this special case. But in a more general case, we have 2 parameters, a spreading factor and a processing gain, and the difference of the 2 depends on the time bandwidth product of the spreading waveform, and thus the design of the spreading waveform itself. Yeah, interference. So this is my last slide for this first lecture, where we introduced the multiple axis scheme for GNSS. So we can also now calculate the signal to noise plus interference ratio, SINR, before the spreading in case of additional interference with power J, so uniformly distributed across the band B. So we are assuming a broadband jamming, for example, of our signal with the same bandwidth as our desired signal. And then the SINR before correlation we can write is P over BN 0 plus J, this power of the jammer. And after despreading, we can see that now the processing gain is modifying this influence of this jamming, yeah? Because the interference is independent from the desired signal, and thus the power is reduced by the processing gain. So this means that for broadband interference, the SINR increases after despreading. The SINR increase after the spreading is dependent on the processing gain. So the higher the processing gain, the better our robustness to broadband interference. And the system design can incorporate now certain interference robustness also. And interestingly, if we have narrowband or partial band interference to C of t, then C of t spreads the jamming signal, because in correlation we multiply C of t with the received interference. So the C of t is spreading the interference now, reducing the absolute or the power level of the signal, but spreading it into a wider band. And thus it appears as wideband Gaussian noise after correlation. So it's not harming us so badly. But okay, this is also in certain levels only. I mean, if the power increases and increases, this will harm us. So, but the processing gain introduces interference robustness, which is an important aspect of GNSS systems. You have in some bands you have to share with other. You have to share the GNSS services are shared with other radar systems and other systems. So you have to live sometimes with some interference. On the other hand, we also experience a lot of jamming, and especially then for safety critical applications, jamming is an important issue. And so the signal design can provide already some robustness. So yeah, thank you very much. So this was the first lecture on the multiple axis of GNSS, and we will proceed after a short break then with spread spectrum ranging. You have questions? Anybody has questions? Okay. Yeah. Ah, yes. Okay. Ah, yeah. Yes. And are the video? Yes. So I can first answer yes, the video recordings will be available later. I can talk about the question about the factor R, separate the difference between the spreading factor. Can you press Control L, please? Here. So we can. One of the questions was if I could explain again what is this factor R here. The factor R is related to the time bandwidth product of B relating the product of B times TC. Yeah. in our case, we assume that BD is fixed, is equivalent to 1/2 TD. So we assume here that B is equivalent to R divided by TC. So B times TC is equivalent to R. In some signals, for example, GPS CA code signal, B times TC is 1. If you assume, for example, a bandwidth of 1.023 megahertz. For example, if you use a BOC11 signal and you use a 4 megahertz two-sided bandwidth or 2 megahertz one-sided bandwidth, the time bandwidth product is 2. So the R is related to this time bandwidth product. So it depends on the choice of B in your receiver, and also depends on the relation between B to the chip duration. And then there was a question about papers about the mismatch. I can comment, if you look up my name, there are some papers on measurements. So we did some modeling of biases. I don't remember the title now, but I can send you these papers. So we did some measurements at the German Aerospace Center. We did some measurements many years ago of different satellites, and we made characterizations of we derived characterizations of GPS payloads. So the transfer function of the satellite, assuming that the model as it is specified in the signal in space interface control document, which is called sysICD of GPS, so we assume that the model is generated on the satellite, and we measured what is the output of the satellite with a calibrated very large antenna. And from this we could derive the transfer function, which means we can derive how the waveform that we receive on Earth is changing or is different from the model as defined in the standard. And there are some papers for all the systems this exists. So the Stanford University, they have worked in the US together with the Air Force, and they have worked on characteristics like this. They're called, sometimes you can find this also under the keyword evil waveforms. People tried also to assess, is this changing over time, this behavior of the payload? This is until today, I think, is not fully clear, but there are there are some measurements already published where you can see changes over time. So this model can be derived by measurements. We will also hear during the workshop about the Galileo High Accuracy Service. And the High Accuracy Service of Galileo has an interesting feature. It provides you with also these measurements of this this model mismatch somehow. It provides you with biases, with measurements made by receivers that measure this. What's the result of this mismatch? Okay, and the service itself provides you with these estimated mismatch biases. The problem always is that this is not, you cannot separate that. I mean, it depends on the receiver also, right? So the mismatch depends on the receiver, because you have after an antenna, you have receiving chain, you have filters in the receiver, and so on. It also depends on what is the choice of your bandwidth in the receiver. So in general, it's a cascade of the satellite system characteristics plus the receiver, and then you have to evaluate at the output what is the result of this mismatch that you use as a model for correlation. And then on the other hand, you have to trade off, am I willing to invest more complexity to implement a more detailed model in my receiver? So you have to make also this choice, saying, oh yeah, I invest this complexity, and then I have no bias anymore, which means that you have to also calibrate your receiver to some extent and so on. So this is a difficult topic, but a very important topic, because these biases, when we talk about sub-decimeter accuracy and decimeter accuracy, they play a large role, especially in precise point positioning, RTK solutions. You have to estimate them. Together with the positioning, you have to estimate all these biases, or you have to have an idea about these biases. And this complicates the process, also gives you a very long convergence time of the algorithms at the moment. So when you want to achieve decimeter accuracy, you have to, and your algorithm starts using the GNSS data until it arrives, until it converges to this accuracy. It takes a very long time, depending on what kind of algorithm you use. This can be even in terms of minutes. And when you lose connection to some of the satellites, you have to reinitialize this again, and this can be somehow cumbersome for, or dangerous for, no, not dangerous, but can be yes, a disadvantage for your application. You have to stop your tractor, for example, again, and have to wait. But okay, there's a lot of algorithms, there's a lot of research out there that trying to improve this situation. And we will hear about the Galileo High Accuracy Service during during this the master class here, about this contribution that the High Accuracy Service makes, because it provides you with these biases, so you can use these biases in your algorithms. Yeah, we will hear later about that. I did that already.
Ah, okay.
Yeah.
So the next one is what real-world jamming techniques have proven to work best for GNSS signal? Jamming, how do they work in principle?
Is it? So what real-world jamming techniques have proven to work best for GNSS signal jamming? How do they work in principle? Yeah, I mean, if you want to make sure to jam a GNSS receiver, you work with broadband interference. So you cover the band with a lot of power, and then a single antenna receiver is blind. You can then switch on the user side, you can switch to a multi-antenna receiver, and the multi-antenna receiver can then implement kind of an SDMA, so the space division multiple access, so you can then separate the jammer from the satellites in space, because you have multiple antennas. With these multiple antennas, you sample the signal not only in time but also in space, and then you can perform, for example, spatial bandpass filtering or some other techniques, and then you can filter out even a broadband interference. But yeah, if the power gets larger and larger and larger, and this is also applied, you can even destroy the receiver also. So there's so much power that the amplifiers in the receiving chain, they go they are saturating, or they even are destroyed. So this is the most secure, maybe. But maybe you meant, maybe the question was targeted to interference mitigation. I mean, in case of broadband interference, I already said this. So I think a multi-antenna receiver is very, very robust already, and this is also the case what's applied for military receivers. There's a lot of techniques for when the bandwidth of the interference gets smaller. So there's like signal, or if it's pulsed interference, for example, you have an interference that is switched on and switched off. Then what you can do is you can throw away the samples with the large power, which is called blanking. Then there's applications for what's called notch filters. You can in frequency domain, you can implement zeros in the filter characteristic of the receiver, and with this you can notch out narrowband interference, for example. So these are the techniques used a lot in civil receivers with single antenna. But okay, single antenna gets, if you get to the point that you have broadband interference with large power, you have no choice anymore. You cannot listen into the signals anymore. The interference is so loud. Then you have to change to a multi-antenna receiver, and you have maybe a more robust, you have definitely more robustness with this. And then, yeah, when you increase the power and increase the number of sources, we didn't talk about that yet. So you can have, instead of only one jammer, you can have 10 jammers. And so, yeah, but this gets more complex and more difficult to implement. I hope I answered this question in a general case.